So we had done oxidation of primary alcohols, right? And the big thing is you need to keep straight the two different groups of oxidants, right? You have your mild oxidants and then you have your strong oxidants, right? Mild oxidants oxidize primary alcohols to aldehydes. Strong oxidants oxidize primary alcohols to carboxylic acids. So, first one here, is that going to be an aldehyde or a carboxylic acid? It's going to be an aldehyde. This carbon right here, that carbon right there. Next one, carboxylic acid or aldehyde? So is KMNO4 a strong oxidant or a mild oxidant? Strong. So strong oxidants are going to oxidize to the carboxylic acid. Right, PCC, is that going to go to the aldehyde or to the carboxylic acid? Aldehyde. Sorry, Swern. I still can't make an E. Third try. There you go. All right, so top one, aldehyde or carboxylic acid? Aldehyde. Chromium oxide, water, is that going to make a carboxylic acid or an aldehyde? Carboxylic acid. And what about the last one? It's strong, so it's going to be a carboxylic acid. All right, so for your primary alcohols, you need to keep straight. If you're using a mild oxidant, it's going to oxidize one time to the aldehyde, or if you're using a strong oxidant, it's going to oxidize that primary alcohol twice to the carboxylic acid. Now, next up is secondary alcohols, and these are way easier, right? In that all your oxidants are going to do the exact same thing. So for secondary alcohols, so they're only oxidized once, and you're going to have no carboxylic acids, right? So they're only oxidized once to the ketone. So kind of regardless of what the oxidant is, right? You have generic oxidant. You're always just going to end up with a ketone. So now your group of 3 strong oxidants and 3 mild oxidants are now all on the same group, right? They all just oxidize secondary alcohols to ketones. So it doesn't matter which one you use, you're going to end up with the same product at the end. Right? They're all going to be oxidized once to the ketone. So you no longer have to keep them separate. You just have like oxidant, make ketone. So now all your oxidants are effectively the same. And the last two to just really drive it home. All right, so they're all going to end up doing effectively the same thing. And the reason is, right, so just so you remember, right, when you have a primary alcohol, right, you have 2 hydrogens on the carbon that has the alcohol. So when you oxidize it, you can either remove 1 hydrogen and make an aldehyde, or you can remove both hydrogens and make a carboxylic acid. When you have a secondary alcohol, there's only 1 hydrogen. And so you only have 1 hydrogen you can remove, so there's only 1 possibility. You only get a ketone, right? There's only 1 oxidation you can pull off. If you have a tertiary alcohol, can't do an oxidation, right? Because there's no hydrogen to remove. So you're limited by the number of hydrogens on the carbon that has your alcohol for the number of oxidations you can do. So it's good. Try to spell this right. I am not. So the last kind of set of reactions we have to do for alcohols are the reactions of vicinal alcohols. All right. So a vicinal diol are just alcohols that are on adjacent carbons. And they do different reactions than just an isolated alcohol. Just, a primary alcohol by itself or a secondary alcohol by itself. We already know what they're going to do, right? They can be oxidized once or twice, right? But if you have vicinal diols, they're able to do different things. The main thing that they're able to do is you're able to cleave vicinal diols. So right, you're going to break a carbon-carbon bond. So there are two reagents that can do this. The first is periodic acid. It's going to turn into secondary alcohol into an aldehyde. Tertiary alcohols into ketones. So this kind of goes against what we said just a second ago. So what happens here is you have your two alcohols, and you add HiO4. Right? And what the periodic acid does is it breaks this carbon-carbon bond between the two alcohols and then oxidizes each alcohol one time. So you go from having one molecule to having two. And you make two aldehydes. Here I have a secondary alcohol and a tertiary alcohol. I break the carbon-carbon bond between them and then oxidize each alcohol one time to make an aldehyde and a ketone. In straight chains, stereochemistry doesn't matter. You're just going to do the same thing kind of regardless of stereochemistry. You're going to break that middle bond, oxidize each carbon one time. In rings, though, the stereochemistry matters. So if you have a ring, only cis diols can do this reaction. So I'm going to break that bond and then oxidize each alcohol one time. Make two aldehydes. I try to draw these basically the way the ring looked initially. So I just kind of try to keep them the same. But you could just as easily draw them like straight, and it's the same thing. Right. Now, if you have a trans alcohol, I'm just going to write no cleavage. I don't want to say there's no reaction because the HiO4 could do another oxidation or do something, but it's not going to break that ring, right? You're not going to be able to break that carbon-carbon bond when they're on opposite sides, when the two alcohols are on opposite sides. The reason for this is how the mechanism works. I'm not going to draw the whole thing, no worries. But when you do this reaction, right, to get your open ring, here, I'll actually add something a little different. Right, you have to make a ring in the mechanism. Right, you need to make a ring. If the two alcohols are on the same side, it's easy for you to make the ring, right? If you think about, like, if you have your pen or your pencil or whatever, and you have your arms on the same side, you can grab onto your pencil and you can make a ring, right? If your arms are on opposite sides of your body, now you can't reach, right? You can't reach that pen to make a ring with your arms. Same thing here when you have a trans diol, right? Now the alcohols are on opposite sides of the ring. They're too far apart, so you might be able to stick the iodide on one oxygen, but it's not going to be able to reach the other oxygen to make the ring that you need to make to open up that carbon-carbon bond. Right, so they always have to be cis so that you're able to make that ring. If they're trans, they're going to do something else. Hopefully, dokely. And then the other way we can do this, we can use KMNO4. It's a stronger oxidant, so the big difference between it and periodic acid is it the secondary alcohols that you have on your vicinal diol, they become carboxylic acids. And your tertiary alcohols still become ketones. Right, so you're going to break your carbon-carbon bond, and now you're going to oxidize those alcohols as many times as you can. So for the secondary alcohols, you can oxidize them all the way up to carboxylic acids. So you can kind of think of it as you're replacing one of the hydrogens you would normally remove with that carbon-carbon bond you're breaking. So you can break the carbon-carbon bond, and then there's still a hydrogen, so the K-4 removes that, so you oxidize it twice. For tertiary alcohols, you break that bond, and the tertiary alcohol can only be oxidized once. So here I'll make a carboxylic acid on this side plus a ketone on the other. Okay, so you're always going to break the molecule into two, or you're always going to break that carbon-carbon bond. You have the same kind of limitation that you want to have cis diols to do the cleavage reaction. So if you have your two alcohols that are cis, all right, we're going to break that carbon-carbon bond. The tertiary alcohol on top gets oxidized once to a ketone. The alcohol on the bottom, the secondary alcohol, gets oxidized to a carboxylic acid. Now again, I will do my best to draw them kind of the way they started out on the exam, but I told the early class if it takes longer than 3 minutes for me to draw the structure and have it not look awful, I'm just going to draw it the straight chain way. Because when you start getting like ketones and carboxylic acids, it's hard to like get space for everything. So if it starts to look really funky, I'm just going to go, this looks too bad. Like my OCD will kick in, and I'll just be like, nope, gotta do it somewhere other way. Right? If the alcohols are trans, then you can't do the cleavage, right? Because they're not cis. But KMNO4 is still going to do as much chemistry as KMNO4 can do, right? So it's going to look at that secondary alcohol and go like, I can oxidize you. And it's going to oxidize that secondary alcohol. Right? It can't oxidize the tertiary alcohol because there's no hydrogen, but it's going to do as much as it can. It's going to be like, I can oxidize the secondary alcohol. Let me oxidize that. Reasonable? So someone had asked in the early section, what if you have a primary alcohol? Like I talk about secondary alcohols and I talk about tertiaries. Why not bring up primaries? The reason is that they do kind of the chemistry you expect, but the pieces that you make are so small that we don't end up worrying about them. They're not things that we actually would want to try to make this way, right? So if you break this, I'm going to oxidize my alcohols each once, and I'm going to make the hydrogens and make it a little bigger, formaldehyde, right? That's just something that you're not going to really want to care about. Same with if you do the same thing with KMNO4. Oops. right? I'm going to make formic acid, or it's going to go all the way to carbonic acid, right? Again, not something that like you're really going to want to care about, right? Because there's just one carbon. So the reason I only worry talk about secondary and tertiary carbons is you get bigger pieces normally, and you care more about those bigger pieces than you do like formaldehyde or formic acid or something. So that's why we focus on secondary, tertiary alcohols. Is just primary alcohols give us really small molecules. You feeling good? All right, cool. All right. Let's do A, B, and C. So what do we got going on up there? What do we need to be able to do here? I need to be able to turn my alcohol into something that I can make a Grignard reagent out of. So what something do I need to turn the alcohol into? So what would B be? So I make my Grignard is a magnesium chloride. So how do I make a Grignard reagent? The B should be an OH just replaced with a chloride, right? So if you think about it, there's a couple of different ways to think about it, but it works right because when you make a Grignard reagent, you just stick a magnesium between the carbon and the halogen that's on the molecule. So if you have a Grignard reagent, you can think about it as just pulling the magnesium out, and that's going to give you the carbon bonded to a halogen. C is going to be magnesium. So how do I turn a primary alcohol into a chloride? Mm-hmm. HCl and zinc chloride. Right, for a primary alcohol, remember, if you add just HCl, that's not good enough. You have to add the zinc chloride to make it go. Right? So we made our Grignard reagent, and now we're using it down here. So what do we know that Grignard reagents react with? They react with ketones and they react with aldehydes, right? So I have a primary alcohol, and a step later it has to react with a Grignard reagent. What would I probably turn that primary alcohol into? One of those two things. Awesome. That is an awesome Jeopardy answer. What is one of those two things? Ghost of Alex Trebek. Too soon? Too soon. So I can't turn a primary alcohol into an aldehyde. That would require, into a ketone. That would require an extra carbon. So I have to make it an aldehyde. Right, so it stands to reason that E is going to be an aldehyde. How can I turn a primary alcohol into an aldehyde? We literally opened the class on this. Des-Martin will work. Yep. Des-Martin, Swern, or PCC, they're all mild oxidants that are going to oxidize that alcohol one time. So I've got this aldehyde. I've got this Grignard reagent. What kind of product am I going to make? I'm going to make an alcohol. What kind of alcohol? Primary, secondary, tertiary, quaternary, which isn't really a thing. What am I going to make up? Kind of alcohol. This is when I mutter under my breath that your test is apparently Monday. So, got to remember stuff. You got to make it secondary, right? An aldehyde has one carbon on it already. You add the organometallic, you add a second carbon to that carbon. So I make a secondary alcohol. Right, so here's my alcohol. Right, so you can see this carbon right here is this carbon right there. And then I have 1, 2, 3, 1, 2, 3. So I have this secondary alcohol. I need to turn it into a bromide. How can I do that? Ah, excellent. So the problem with HBr here is that HBr goes through a carbocation, right? So that can lead to rearrangement. So if you were to use HBr, I'm going to jump off this slide. I'll be right back. Right. So if you were to use HBr, you would make that bromide because you would protonate your alcohol. It would leave, you'd make a secondary carbocation, right? Whenever you make a secondary carbocation, you have to look at it and say, can this rearrange? And in this case, it can. Right? You move this hydrogen. So then you make the tertiary carbocation, and that's what your bromide ultimately adds to. So in like simple cases where you don't have to worry about rearrangement, HBr 100% great. But because there's a possibility of rearrangement, there's another reagent we can use. What's that reagent? Yep. And pyridine, yep. So now I've got this alkyl bromide, and in the end I have a tertiary alcohol, right? And you can see here, right, that part of the molecule is already there. We've already made that. So we just have to add this, make it orange, this piece right here. So how do you know how to make a tertiary alcohol? Yes, sir. Do I have an extra methyl? Oh, I do. Oops. Fuel shade. Sorry. Extra methyl. Sorry. There you go. My bad. So how do I make a tertiary alcohol? So we made a secondary alcohol by adding an organometallic to an aldehyde. So we can make a tertiary alcohol by adding an organometallic to a ketone. I thought I heard someone mutter ketone. We'll blame the mask. Excellent. Be proud. Right? So you can add it to a ketone. So I need to add it to a ketone that has 3 carbons, right? Because in orange there I have 1, 2, 3 carbons. It's hard to see that 3. I promise you it's a 3. Right? So that could just be this, then H plus. Right? So I'm going to, you could make this a Grignard. We've already done one of those. So let's say it's a lithium. How can I turn a bromide into a lithium? It's just lithium metal. That was an easy one. Guys overthought it. So how do you know how to put 2 bromines on something? This is some sweet, sweet organic one. It's just Br2, right? And what does the Br2 have to react with? Like what functional group? Hmm? Yeah, double bond. Yeah, so that's react with a double bond. So where those 2 bromines are, you have to have them, you have to have a double bond, right? So that each carbon has a bromine on it was part of a double bond before. And how can I turn my alcohol into a double bond? Gonna work? POCl3 and pyridine, or you could use sulfuric acid and heat, or phosphoric acid and heat. Any of those 3, or whichever one I would like put in the multitude of reagents that you would have to pick from. Again, my goal is to not put like 2 reagents that are going to do the same thing. So you kind of have to know all 3. Because if I pick phosphoric acid and heat, and that's the one you chose to forget, then you're screwed. So you have to make sure you know all of them. Yay! And usually, like I said, I will put like a something from organic one. It would either come like way at the front or way at the end of a synthesis. I wouldn't stick it like in the middle because I think that's just harder, right? But I could, do something like this, right? Pretend this was longer, but you know how to make a carboxylic acid, right? What is the one way you know how to make a carboxylic acid? Well, you know two. What's one way you can do it from uh, keeping in mind we're talking about alcohol oxidations? KMNO4, right? And that would have to react with what? What? KMNO4 plus what equals a carboxylic acid? A primary alcohol, right? So we could say, hey, we have KMNO4, and I have this primary alcohol. How do you turn a double bond into a primary alcohol? And that's how you go from alcohol to double bond. I need to go the other way. Write it backwards. No, we can't just write the reagent backwards. We can't go Cl3OP and be like, yep, we're good. No, no, no. So this is the organic one thing, right? So, and we covered this even when we started alcohols, right? Ways we already know how to make alcohols, and this would be like BH3, H2O, water, and hydroxide, right? So that is the way you make the anti-Markovnikov alcohol, right? So I get sick that at the beginning, right? And then there could be a longer synthesis after it, and if you're like, I don't remember that at all, that's organic one. I like forgot all that stuff, right? You could then just start from oh god, you could then just start from here, right? And be like, okay, I don't know A, B, and C, but I could pick up, I could pick up D, E, F, G, yada yada yada, further on down the line, right? So how do I, how would I make this ester? Keeping in mind that there's a double bond involved, meaning we don't want to just take like sulfuric acid and the alcohol and heat the crap out of it. So it's the other way we know how to make an ester. So we know, right, that this part of the ester comes from an alcohol, right? Right? So now, how can I put that alcohol onto my carboxylic acid? How can I make that an ester? Four letters and a number. Give me an O? Oh, yeah, we got an O. Not the POCl3, so you're close though. Something OCl and a number. You already said the number three. You said POCl3. Hmm? Two? All right, two it is. Thionyl chloride is SOCl2. Right? That's the way you can make Esters would happen to use strong acid. Oh man, chat might have beat you to it. All right, and with that, that's class. So I'll see you guys next time.